Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic we're going to look at Neumann and insulated boundary conditions. In this topic we will review Neumann boundary conditions, and we will see how we can approximate the derivative using the formula from calculus combined with a Neumann condition to eliminate one of the unknowns, be it either the left-hand endpoint or the right-hand endpoint. This will give us a system of n-1 equations and n-1 unknowns, and we can author a solution in MATLAB using this approach. We will observe that there are weaknesses in such an approach, and we will therefore consider and observe the effect of using a superior order h squared approach. So up until this point, for boundary value problems, we've looked at approximating solutions when there are Dirichlet boundary conditions, or fixed boundary conditions. That is, the values of the solution at A and B, the endpoints, are given in the problem. Now, you'll recall that these fixed boundary conditions affected the first and the last of the n-1 equations. So in the first case, u0 was deemed to be equal to u sub a, and therefore that term could be brought to the right-hand side, and for the last, u sub n is deemed to be equal to bu sub b, and thus r sub n-1 times u sub n, now u sub b, could also be brought to the right-hand side. And then we had a system of n-1 equations in n-1 unknowns, which we solved and gave us the solution. However, at the start of the topic, we discussed that there are more general conditions, such as Neumann conditions, where we specify the derivative. For example, we may have an insulated boundary, in which case the derivative is 0. Or perhaps the boundary value has a derivative that is fixed, perhaps due to a rate of power dissipation. How are we going to deal with this to find an approximation? So now we are no longer finding a solution that is fixed at two endpoints, but rather a solution that may be fixed at one endpoint, but has a slope that is specified at the other endpoint. Suppose that we have a Neumann boundary condition at x equals a. So the slope at the left-hand endpoint is fixed and given. Well, we still have that first equation, and that first equation still has u0, u1, and u2. But how do we eliminate the u0? After all, if we do not eliminate u0 from this equation, then we will have fewer equations than we have unknowns. So somehow we have to convert the Neumann boundary condition into an expression that allows us to eliminate the unknown u0. Well, recall that we've been using divided difference approximations of the derivative. So we know that an approximation of the derivative at the left-hand endpoint is given by u at a plus h minus u at a all over h. And that is the value that is specified in the boundary condition, u sub a prime. But wait a second, u at a is approximately equal to u0. Again, we're trying to approximate u sub a by u0. And u at a plus h is being approximated by u1. So substituting these two into the above equation gives us that the difference between u1 and u0 all over h is approximately equal to that slope. Well, we can solve this for u0. And assuming that it's exact, then u0 is equal to u1 minus the slope at the left-hand endpoint times h. Well, that sort of makes sense because, after all, that is the derivative, or at least close to the derivative at the left-hand endpoint. So now we have an expression where we describe u0 in terms of u1 plus the given Neumann derivative and h, both of which are known. So thus, if we have a left-hand Neumann condition, then we have the equation, and we have an equation that describes u0 in terms of u1. So previously we replaced u0 with u sub a and moved it to the other side. Now we're going to replace u0 with the expression in the second equation. Substituting that second equation into the first and simplifying yields the following expression, and therefore we can bring the known values to the right-hand side and collect on u1. That gives us this expression here. So now we have updated the coefficient in front of u1, and we have an updated value on the right-hand vector. Thus, the entry 1, 1 of the matrix needs to be updated, and the first entry of the target vector needs to be updated. Similarly, we can do the same thing at the right-hand boundary value. We find u sub n as an expression in terms of u sub n minus 1 and the slope at the right-hand endpoint times h. Substituting the second equation into the first yields this expression when simplified. And now we have to update the last entry of the matrix, the n minus first by n minus first entry of that matrix. And we also have to update the last entry of the target vector. All right, let us include Neumann conditions in our boundary value problem solver. We're going to add a new parameter, specifically Dirichlet, and that will be a vector of two entries that are either true or false. If the first entry is true, the left-hand endpoint is a Dirichlet condition. If it's false, it's not a Dirichlet condition, and therefore it is a Neumann condition. And the same for the second entry of that vector. Again, h is the same, p, q, and r are the same, the x values are the same, and then we create our matrix without updating any entries. So this just has the entries p, q, and r in the appropriate locations. Next, we create the right-hand vector, which initially is just twice the forcing function evaluated at each of the interior x values, each multiplied by h squared. So now we're going to check. If the left-hand condition is assumed to is given as Dirichlet, then we will update the target vector as previously done. However, if it is not a Dirichlet condition, i.e. it is a Neumann condition, then we have to update the last equation as given above. So basically that requires us to add p evaluated at x1 onto the entry 1, 1 of the matrix, and we have to add p evaluated at the first interior point times the boundary times h to the first entry of the target vector. All right. Next, if the right-hand boundary condition is Dirichlet, then we just update the target vector as before. If it is not, it's Neumann. And what did we have to do? Well, again, we had to add r evaluated at the right-hand, at the last interior x value to the last entry of that matrix. And we also had to update the last entry of the target vector. All right. So that is our implementation. Next, we solve this system of linear equations, and that gives us the approximations at each of the interior points. So let us add the first x value and the last x value onto the vector of x values. So now we have all the entries going from a to b in steps or increments of size h. Now, If the first condition was Dirichlet, then the left-hand value, the value at A, is given in the problem. However, if it's a Neumann condition, then U0, the value at the left-hand endpoint, is given by the expression we calculated. So that's what we will use here. Similarly, if the right-hand condition is Dirichlet, the value at the right-hand endpoint is given. Otherwise, again, we use the same expression as before to determine the value of the solution at the right-hand endpoint. And as you will recall in MATLAB, when the function exits, whatever value the return values have, that is what is returned. And you will recall that the return values for this function were xs, the x's, and us, the u's. All right. Now we can call our function with the appropriate arguments with the function of the second derivative, the function coefficient of the first derivative, and the function coefficient of the unknown u of x. Next, the forcing function sine, the interval ab, -1, 1, the left-hand boundary condition, and the right-hand boundary condition, and then a pair false true, indicating that the left-hand boundary condition is Neumann, the right-hand boundary condition is Dirichlet, and we are using 10 subintervals. Now solving this system of linear equations yields these 9 values. These are the approximations at the interior points. So for example, once again, this fourth entry is the approximation of u at -0.2, while this entry, the last one, is the approximation of u at 0.8. Also, we have that u at 1 is equal to 2. After all, the right-hand boundary condition was a Dirichlet boundary condition and therefore given. However, the left-hand value is approximated by our approximation we described previously, and therefore u at -1 is approximately equal to that value we see here, 1.07. All right, a plot of the approximation we just calculated is shown on the right here, and it seems to have approximately the derivative we've desired. However, the plot on the left is the solution we found previously to the Dirichlet problem with the two fixed boundary conditions, u at -1 is equal to 1 and u at 1 is equal to 2. The slope you see on the right-hand side was specifically chosen to be exactly the slope of the solution to the problem on the left that we've already calculated. So you can see that the values of the approximation on the left are much better than the approximations on the right. The errors are much larger on the right when we used the Neumann conditions. Now, is that a consequence of using Neumann conditions, or did we do something wrong? All right, so on the left-hand side was what we calculated previously using two Dirichlet conditions. The conditions on the right are equivalent to the conditions on the left, but we solved the problem with a Neumann condition on the left-hand boundary, and we get significantly larger error. Can you think why that might be? So what happened? Why is our solution here so poor compared to essentially the same problem we solved in the last set of slides with Dirichlet conditions? Well, you're going to remember that when we converted the ordinary differential equation into a finite difference equation, we substituted approximations of the derivative and the second derivative that were order h squared. However, when we were approximating the derivatives at the left-hand endpoint and the right-hand endpoint, we used order h approximations. Because remember, u at a plus h minus u at a all over h has an error that is order h. And because all of the equations are intimately related via a system of n-1 equations and n-1 unknowns, consequently, we get the worst case performance. And the worst case performance is that the error is going to be order h. So if you mix a good estimator, one that is order h squared, with one that is poor, such as this one, which is order h, then the overall result is going to be order h. That's unfortunate. You will recall, however, that we did indeed introduce both a forward divided difference approximation of the derivative and a backwards divided difference approximation of the derivative, both of which were order h squared. Again, both of these approximations used 3 terms, not just 2. Consequently, we can solve each of these for u0 and un respectively. We can then substitute u0 into the first equation, un into the last equation, as shown here, and having substituted them and simplified, we get that the first equation is now modified to look like this, and the last equation is modified to look like that. All we've done is algebra and substitutions. All right, so nothing changes here in our function. Everything's the same. We set up the matrix as per before. We set up P, Q, and R, the x values. Similarly, we set up the target vector as before. Now, only if the left-hand boundary condition is Neumann do we update the matrix. Now we have to update 2 entries of the matrix, and we update the target vector as well. And if the right-hand boundary condition is Neumann, then again, we update the last 2 entries of that matrix as well as the last entry of the target vector. We solve the system of linear equations. We add both a and b to the vector of x values, and if the left-hand boundary condition is Neumann, then we have a slightly more complex expression for approximating the value of the solution at the left-hand boundary point, and we have a slightly more complex expression approximating the value of the right-hand boundary, again, if the right-hand boundary point is a Neumann condition. All right, now if we do the same thing, call the same function, solve the modified system of linear equations, the order h squared version, we now get this as the approximations. On top of that, u at 1, the right-hand boundary, is still 2, but u at -1 is much closer to 1. In fact, significantly closer. Indeed, the order h approximation appears on the left, whereas the modified version, the order h squared version, a solution appears on the right. Notice how much closer the approximation is. So once again, it's important to remember it's bad to mix order h and order h squared approximations because the order h approximation will decimate any benefit you got from using the order h squared approximation. Consequently, when we use the order h squared approximation everywhere, then the final result was equally good everywhere. Now recall that insulated boundary conditions are simply Neumann conditions when the specified derivative is given as 0. Consequently, only the matrix is modified as the change to the target vector is 0. So if the left-hand boundary is insulated, that expression is 0, and if the right-hand boundary is insulated, that expression goes to 0. Following this topic, you now have a better understanding of what Neumann conditions are. You understand that better approximations cannot compensate for poorer approximations. If we mix order h squared and order h approximations, the final result will be order h. Also, you know how to approximate a boundary value problem with Neumann conditions where all terms are order h squared, and you have gone through an implementation of such a solver in MATLAB. You have also now seen an example where we do solve a Neumann boundary condition. Acknowledgements, the colophon, and a disclaimer. Cheers!